Okay, hello everyone, this is Mr. Steele, and I'm again trying to make some videos with this new iPad that was given to me for use and testing out by Mrs. Hubbard in the Green Academy. So today I'm going to try to fill in some of the blanks for some students that might have missed some stuff in Honors Pre-Cal last year. Particularly, I'm looking at trying to get a basic idea of what a limit is. It's not going to be as intense a look as we'll get in the first couple weeks of class, although you've already kind of seen some of that stuff before in Honors Pre-Cal, or even Honors Algebra 2. But at the same time, just kind of looking at some of these things, and in particular, like this idea of a limit. Like, what does this come from? Like, how much understanding, are you expected to have when you come into calculus on the first day, when we start the chapter 1 in the book, which is titled Limits. So what we're looking at here is a place where where Honors Pre-Cal and Honors Algebra 2 both introduce the idea of limits in context of rational functions. So right here, we've got a rational function, y equals x plus 3 over x minus 2. And what we're going to do is we're going to graph that and then look at some limits that we can analyze. In particular, the reason we choose rational functions to analyze limits for is because we can look at some places where there's some interesting behavior. So, of course, stuff that you might remember to graph this guy, which I'll just do in green over here, is the denominator. Kind of gives us what I call the Chuck Norris numbers, vertical asymptotes. In this case, we're going to have a vertical asymptote at x equals 2. So normally I would graph that in red, so let me do that. At x equals 2. There's a vertical line that can't be touched. Yeah, still learning how to use this. And then second, we can also get kind of a 0 here. And there's going to be a 0 anywhere that makes the numerator equal to 0. In particular, our 0 here is going to be at negative 3 comma 0. Again, it's just graphing it for the sake of getting some good stuff here. When in doubt, just make the dot bigger. Okay, what else can we get? We can also talk about an EBA. The EBA, or the End Behavior Asymptote, something we look at a lot, is what we get when we divide the top by the bottom. It describes what's happening at the ends. It's a very important concept for limits. In this case, if we do long division, we'll see that our EBA is y equals 1, which means we'll have it's not necessarily the best graphed dashed line in the history of the universe, but it's not the worst one either. So there we go, there's kind of our basic setup. What else do we have? Well, we also could find the y-intercept, which in this case is going to be 0, comma, negative 1 and 1/2. I like mixed numbers. And so what do we got? We get another point right there. So now what does this give us? Well, we've got the basic shape right here. On the other side, we'd have to find a single point. So this is kind of the old way of doing it. We didn't have a perfect setup. So when I look for a point, I pick a point on the other side of the vertical asymptote. In this case, it's going to be 3. And if I plug 3 in, I'll get 6 over 1, which is 3 comma 6. So there's another point. And now, with that said, I can graph my entire rational function. Okay, so your mind's probably thinking, okay, that's a lot of work just to graph a rational function. Done that 2 years in a row. How is that important? Well, the fact is, by having this rational function graphed, we can analyze particular limits, like what kind of behavior are happening at certain points. And if you think about it, the points that are most interesting, or the places that are most interesting to look at, are first of all the vertical asymptote. We're going to take a look at what's happening there and describe it using limits, and then also what's happening at the ends, just because those are places that are either on the graph where something weird's happening, or they're just kind of something that's supposed to be descriptive enough that it could be graphed forever onward afterwards. So looking at those guys, let's start with the ones on the outside. Let's start with still trying to figure this out. So let's go with this guy. What is the limit as x goes to positive infinity of this guy? And we'll say of y. So now what you're being asked when you're asked something like the limit as x goes to infinity is they're saying, how can you describe the behavior that's happening as you take this graph closer and closer to positive infinity? Well, positive infinity isn't actually a place. Like, it's not like we can just go 1, 2, 3, 17, 42, positive infinity, and we're just there. It's actually just kind of an idea. So we just have to look on our graph. And fortunately, we already kind of have a description of that. We have that the end behavior is y equals 1, which means that as we get closer and closer to x equals positive infinity in the x's, so as we travel along and get bigger and bigger x values, what happens? If you remember, our graph just gets closer and closer to our EBA, y equals 1. So in fact, the limit as x goes to infinity, positive infinity, is equal to 1. And we could see, very similarly, that the limit as x goes to negative infinity of y is also equal to positive 1 for the same reason. As we pick smaller and smaller x values, our graph eventually goes towards 1. Like at a certain point it becomes so darn close it might as well just be 1. So that's one way we can talk about limits. Like one idea of limit is exactly the end behavior, or in this case the end behavior asymptote. That is an idea or a notion of limits that we can look at. The second thing that we can talk about is what's happening as far as behavior around the vertical asymptote. So in particular we'd want to ask ourselves the question, what happens as x gets close to our vertical asymptote's value of 2? So what would we say? Well, what we can look at is we can kind of see that there's a problem here. If we look from the right, the values, or the function value is getting bigger and 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 bigger. So that's one thing, but from this side, notice we've got another problem. Like the value is getting smaller and smaller and smaller. So the first thing that we can say is that this thing does not exist. Like the reason it doesn't exist is, we'll talk about it more when we get deeper into calculus. The biggest reason is that it doesn't exist because it's going two separate places. We can't say anything about the behavior at 2 except that something weird's happening. So in fact we just say that the limit does not exist. Now at the same time, there is some stuff that we can talk about if we restrict it a little bit. Like what if we say instead of the limit as x goes to 2, what if we want the 2's coming from the left side? And we'll use this notation. What is the limit as x goes to 2 from the left side? So this means from left. The reason this works is, well, if we're not worried about what's happening on the right side of the vertical asymptote, we're just looking on the left, then maybe we can, get a little bit better description. And in fact we can. Like take a look. If we go from the left side, that's over here, as we get closer and closer and closer and closer and closer, it's going, like it's just getting smaller and smaller. So in fact, if we want to get smaller and smaller, we can just say that it's going towards negative infinity. It's getting really, really negative, or really, really small. Now on the other side, on the flip side, the limit as x goes to 2 from the right side, or the positive side, is going to be somewhat different. Let's take a look. On the right side, if we're going to the right, you'll notice that's where we see that behavior happening. It's getting bigger and bigger and bigger and bigger, and no, it's not approaching 42 as nice as that would be. It's actually approaching positive infinity, or some people would even just write infinity. And there we go. We can actually see that we can use this notation. Sorry, I should... Still figuring out the kinks here. Can use this notation to describe some behaviors that otherwise are just kind of hard to describe. We just kind of say things like, it's sort of getting close to that, or it's going up, or it's getting bigger. Like here we've got some actual notations. We're saying that the limit as x goes to positive infinity, so as it goes to the right, what's happening? Well, it's getting close to 1. The limit as it goes to negative infinity, so as it's going left, so that was right, this is left, limit as it goes towards negative infinity is also going to 1. That's the end behavior that we recognize in the function. Next we can say that as we look at x values really close to 2 on the function, well, stuff's happening, but two different things are happening on each side. On the one side we've got it going down, on the other side we've got it going up. So in fact we can say that there is no limit. There's no real behavior that's consistent from both sides, or at that one place. And of course we can see that there's nothing happening at that one place. It's a vertical asymptote. What we can do though is restrict it from one direction or the other. If we go from the left side, we can see that it's going down. You can describe it as saying it's going towards negative infinity. If it's going from the right side, we can see it's getting bigger and bigger, going towards positive infinity. So again, this isn't perfect. This is just kind of an off the top of my head look at the idea of a limit that you might want coming into calculus in August. But either way, hopefully it's been a helpful little discourse for you. And had I been able to find anything on Khan Academy, I would have just pointed you to that. But instead, you get my discussion here on the iPad. So, enjoy.